Hello, this is the third FRQ of the Unit 11 project. Okay, let's get right into it. So this is a really involved FRQ, a lot of physics facts we have to know, um, and a lot of relevant equations. So first we need to know Coulomb's law. Force is KQ1 Q2 over R squared, and that's going to mean that force is proportional to 1 over r squared. We need to know electric potential energy is U equals K Q1 Q2 over R. We're going to need to know work is change in potential energy. Conducting sphere, the electric field is E equals KQ over R squared. And then potential of an isolating sphere, KQ over R. And physics fact is that connected conductors, they're going to have the same potential. And then another one is that inside the conductor, an electric field will be 0. So the enclosed Q enclosed will equal 0. And then we're also going to need to know Ohm's law, I R. And then also RC decay. That's I over T is a function of time. I naught E to the negative T RC. Okay, so with all those in mind, let's get started. Okay, describe the acceleration of sphere Y as sphere Y is brought closer to X. Well, let's look at the forces on Y. Well, so there's a constant F towards X, and then there's going to be an electric repulsion away from X. And that's going to be two Q times Q over R squared away from X. And as Y approaches, our R is getting smaller, and that would make this go up because it's in the denominator. And then if our net force, that's F minus Fe. So if our Fe is going up and we're subtracting it, then our net force is going to go down. And if our net force goes on, we know from Isaac Newton, net force equals ma, and find acceleration, a equals. And if our F net is going down, and that's in the numerator, our acceleration is going to go down. So our the acceleration of sphere Y is going to decrease as it's brought closer to X. So our answer today is decrease. Now, we're going to use a work equation to answer B. So the sphere is plus 2Q. Okay, so in both cases, they're starting and stopping from rest and are work is just their change in potential energy. So let's write that out. U final minus U initial. So for say work, is R2 greater than, less than? Okay, so it would be our okay, so we're gonna use our potential energy formula times Q over R1, and then minus initial K, because our radius is changing, over R initial. And then we're gonna do it with 2Q that's our R2. So, and we know they have the same, that equals. So we can compare our radiuses. So if we solve for both, set them equal 2Q squared 2Q squared over R1, and that's gonna be Q squared. And then we see from that R2 equals 2R1, and 2R1 is of course greater than R1. You can cross multiply or just see that. For them to equal each other, you would need R2 to equal 2R1. It cancels. So that means that R2 is greater than R1. So that's our answer to B. Now we get this drawn. The electric field. Well, this is pretty easy, as we can just use our electric field equation. So E A equals K Q R squared R A, should say. And then EB equals K Q RB squared. And our RB squared equals 2RA squared. And that's going to be KQ for RA squared. So that equals EA 4. So the electric field at the surface of sphere A is going to be greater than the electric field at surface of sphere V, because B is 4 times smaller, and because a smaller radius will make a stronger field at the surface. And yeah, immediately after the switch is closed, is there current in switch S? Well, let's see. We could find our change in V initially. That's KQ over RA. And oh, actually no. This wouldn't be just be R. And then this is how we calculate change in our VB, KQ to RA. And that's going to be the same as VA over 2. So that means our change in V is going to, it won't be 0. It'll be VA minus VA over 2, which is just VA over 2. And so it's going from a higher to lower potential, and that means there's going to be current flowing from A to B. So there definitely will be current in switch S. And the direction would be from higher to lower. Let's pause here, and then this will be part 1, and we'll do 2 parts because I'm at a 15-minute max on the screen panel.